nanohub.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
So let's get started. Today we'll be talking about bipolar junction transistor and how it is designed. This is lecture 2 on that topic, and in the first lecture regarding bipolar junction transistor and how it is designed, we talked about the problems of classical transistor. Now I don't want to overemphasize it because of course before people got into this problem, there were 25 good years, meaning that around from early 1950s to late or early 1980s, transistors were designed exactly the way I described in the first class. Essentially all silicon transistors and 3 regions, emitter, base and collector, essentially all silicon. Early days there were a few germanium transistors, but subsequently silicon was more robust and more easily processed. So that took over. So this had a good run. This classical transistor had a good run, but starting from early 1980s, this classical transistor ran out of steam, and subsequently many new innovations, a series of innovations came along. One had to do with polysilicon emitter, replacing the emitter instead of having a silicon, which is single crystalline, having multiple crystals of polysilicon and polycrystals of silicon. And this was an accidental discovery. And it turned out, and people could have easily thrown it out without realizing that they had a great thing. And that, in fact, at IBM changed the ball game altogether again in early 1980s. But the short base transistor is that people kept improving on polysilicon transistors for many years. But by mid-1990s, then transistor has sort of hit its limit in terms of bipolar junction transistors, of how thin a base you could possibly have. And I want to explain those things for DC characteristics and talk a little bit about large signal and small signal high frequency response before I conclude. So we are talking about DC bipolar junction transistor characteristics. So I have already explained this particular expression for current gain. You remember beta is the common emitter current gain, that if you put a certain amount of base current, how many times does it get amplified before it gets to the collector, right? Base current is small, and typically these numbers are on the order of 100 to 1000. You don't want it very high because then the transistor will become unstable in the circuit context. And we saw that this gain is related to some intrinsic transistor parameters like the doping of the emitter and the base, the width of the base and the emitter regions, and of course the diffusion coefficient, means how fast the electrons go. You see that's on the numerator, D sub n. So if the electron goes fast, that means I have a lot of collector current, and if somehow the holes which are back emitted base current, if that goes slow, then that's a good thing for me. And overall, I will have a great beta DC based on these parameters. Now, I have explained the trade-offs in last class, and I hope you remember. The trade-offs are such that first, if you assume that if you have a given emitter doping, start there, then so that you want to increase as high as possible without band gap narrowing. What is band gap narrowing? That if you dope it very high, then the band gap that you originally had, that begins to narrow because the dopant state itself then can carry current so the electrons can hop from one dopant to the next, and instead of really taking the highway, it can essentially tunnel through the one state to the next one. And so therefore the effective gap you have is little less, and you can see the gap enters this picture through Ni squared because that has the gap in the exponent. As a result, small changes in the gap, even 0.1 eV, can have dramatic effect on gain because of the band gap narrowing. That is something you do not want to have. The second is that once you have decided on an emitter doping, then you make the base doping as low as possible. But you shouldn't do it too low. The reason is then there will be current crowding. It will be very resistive, and therefore currents will only go through the corners of the emitter and it will not flow uniformly. Do you remember? That's why we had interdigitated structures last time. And similarly, early effect. Early effect is that with little change in the emitter voltage, the base width gets modulated quite a bit, and therefore the gain is no longer constant. So we want to avoid that. And finally, let's say you have decided on a base doping based on these considerations, and then you talk about collector doping. Again, you want to have as small as possible, but if you have it too small, what will happen? That this is an NPN transistor. That means the depletion region in the collector is p-type, right? It's Nd plus. And if you flow a lot of electrons in, then it can completely suppress that charge and the base may be pushed out of that junction. As a result, that's called the Kark effect, and that you want to avoid because that limits high frequency response, as we'll show you today. And finally, the base width as thin as possible, because do you see WB, if you could make WB small, then your gain goes up. So that's something you want to make it small. Now, given these considerations, as I mentioned, that there are not too many things you can do, right? You can play with the three dopings, but sort of constrained by various issues. So then people began to look around and see if there's something they could do to improve performance. So the one was graded base transport. I will come to that, where the WB, you do something about the WB. Instead of making it a neutral region, you make an electric field in it so that the electrons can zip through the base a little faster because you have electric field. So that's graded base transport. We'll talk about it in the next lecture, not this one. The second one, the topic that I'll talk about today, is how polysilicon transistor effectively suppresses D sub P, effectively reduces it, and as a result, your gain goes up. As I said, that was an accidental discovery in 1978-79 at that time. The third one is manipulating this NIB and NIE, and that will be done with heterojunction bipolar transistor. And you know, a couple of years ago, there was a Nobel Prize for this work, just for that term, manipulating it, and therefore all the cell phones and very high frequency circuits you have many times use a version of a transistor which is called heterojunction bipolar transistor. And those, Kromer got Nobel Prize for it, and we will discuss it in the next two classes. And then, of course, the classical Shockley transistors. And let me start by talking about the polysilicon emitter and the innovation that went with it. Now, all modern transistors have polysilicon emitter. The wing-shaped blue region that you see in the top is actually a polysilicon. So polysilicon means that instead of growing it at high temperature, where the material is single crystalline, do you remember all the atoms in their places, the Bravais lattice, do you remember those things? Long time ago. So those Bravais lattices and all those things. So we are talking about the green region that you see just below the wing, and a little blue region over there. So those are single crystalline, but the wing region itself is a polysilicon material or polycrystalline material. Do you see how the base contact is coming through the green? And you can also see how the collector contact contacts the bottom substrate, and therefore the current flows vertically. So we will again turn it over, flip it 90 degrees and look at these characteristics. Now the hatched region that I show here is the polysilicon emitter. So now emitter has two pieces. One piece is this darker blue, N plus, that's single crystalline, and another piece is this hatcheted region, that is polycrystalline material, and we will see how it works. So this is how it works. What polysilicon transistor does is the following. Once you have, you remember, what we are trying to do is increase gain, but we are trying to increase gain by keeping the collector current the same, but by suppressing the base current. So what I am going to show you is how to suppress the base current, because you know, gain is either you can increase the numerator or you can decrease the denominator. Either way it's fine, so long you are just looking for gain. And so what we will show you here is how to suppress the base current. Now you know how the base current comes around, right? So you have holes coming in from the base contact, which is shown here in the middle, in the P region, green P region, and okay. So once there is an animation which will come a little bit later, I assume. Before I get there, so the holes will go from the P to N plus region and flow out through the emitter contact. Now when it does so, if I look at the hole profile, then I see at one end I have P1. This is the exponentially increasing part because the barrier has been reduced. But the really interesting issue is, you see, the P2 is not 0. If I had a metal contact, then I know that the P2, which is the other end, the concentration should have been 0. What polysilicon does is that it limits the velocity at which electrons can go. So it's like a surface recombination velocity, and it is not infinite, unlike metal. As a result, because it has finite Vs, the P sub 2, which is on the other end at the polysilicon junction, is not 0. So in that case, you can immediately see the current will be a little lower, right? Because the slope of this P1 minus P2 for a given width, that has actually been smaller, and as a result I will have less current. That's the physics. There's nothing more to it. I will do a few lines of algebra, but that's the physics, that I have been able to reduce the slope. So first of all, if you have polysilicon emitter, I have I sub P because I'm talking about holes. I have a E in the subscript because I'm talking about holes going into the emitter, and poly because I am in the presence of poly. So those three things are. Do you see minus Q d sub P, P1 minus P2 divided by WE? What is that? P1 minus P2 divided by WE, that is dP dx, right? Do you remember minus Q dP dP dx? So P1 minus P2 divided by W. That's my current. Now, that current must be equal to whatever rate at which polysilicon can take it out. And polysilicon takes it out as minus Q V sub S, which is the surface recombination velocity. Here, it's not really recombining at the surface. It is very different from the previous case that we saw, right? Surface Shockley-Reed-Hall. Do you remember in that case we had a surface recombination velocity? It is not that. It just limits the velocity at which electrons can escape to the polysilicon, multiplied by P2, because that's the concentration I have. Can I solve for P2 now? I think I can. That's the ratio, P2 divided by P1, and that's related to the diffusion coefficient and the surface recombination velocity. Do you agree with this statement? Does it look right? Do you see? If the surface recombination velocity was very large, like metal, then in that expression, Vs should have been infinity, right? Let's say, relatively speaking. If that's the case, what would have been the value for P2? That would have been 0. Do you see that? And that would have been 0. That says that indeed, if it's a metal, then the P2 must be 0. Okay. Now, we can now easily calculate, because I have P2, I can put it in that expression, minus Q V sub S multiplied by P2, can put it in and can calculate the current. Do I know P1, by the way? What is P1? This is Ni squared divided by Ne exponential of that voltage minus 1, right? That's the P1, the junction. So I already know P1, V sub S is a material property. and the diffusion coefficient and the emitter width, these are all I know. So therefore, I could easily calculate this current. Now, if I did not have polysilicon, then if you go back, what we would have done is P1 minus 0. Instead of P1 minus P2, I would have P1 minus 0 divided by WE. Again, the same thing. So the difference between when you have poly and when you have just pure silicon is that this, instead of having just the diffusion coefficient divided by WE, that velocity, I have a more complicated combination over here. Now, if I take a ratio of these two currents, that if I have polysilicon emitter versus if I don't, in that case, what would be the ratio? I simply take that, divide this one from the top to the one in the middle, and I get this ratio. Now, first of all, does it make sense? Assume first Vs is infinity. That is, my poly is so good that it's taking all the electrons out. If Vs is infinity, what is this expression? This expression is 1. So therefore, you haven't improved anything. On the other hand, assume that Vs is very small. If Vs is very small, that is, poly is blocking all the current, in that case, the second term on the numerator or denominator would be 0 compared to the first one. And you can see if Vs is very small, then the poly current, the base current, will be minuscule. So in that process, I have suppressed the base current. That's what we are trying to do. Now, as far as electron current is concerned, going over from the emitter to the base to the collector, well, no problem, because I haven't really changed anything. There's no poly over there in the junction. And so in that case, I will simply write the same expression, N1 minus 0 divided by WB, that is dN dx, and then Q multiplied by dN. So therefore, I will have that current and correspondingly the N1 value. You already know that N1 value. So therefore, I am ready to compute the gain in the presence of polysilicon transistor. Now, one thing I will ask you to think about is that does the poly only suppress the whole current, which is going in that direction, but doesn't do anything to the electron current? Because electron current is also coming through the poly. And why it didn't do anything, that's something you should think about. So that was supposed to be the animation which is supposed to say that the electron actually flows from the base side to the emitter side through that contact, and that's the expression we tried to derive. Okay, now let's calculate the gain. So the whole current is essentially all that is there is to the base current. Why is that? Because the amount of base current flowing to the collector is minuscule. Do you agree? Because base is collector is actually reverse bias. So it has a huge barrier on the collector side, but a very little barrier to the emitter side. And as a result, the base current is essentially entirely is due to the flow of holes. And this is something I have already shown you in the last slide. Now let's think about it. So I want to calculate the gain in the presence of polysilicon. It is IC, the collector current, divided by IB in the presence of poly, the base current in the presence of poly. I could divide and multiply with the base current in silicon. You see, in the last term, I have IBSI, that's in silicon. So divide and multiply, it's the same thing. But fortunately, I know the expression for the first one, IC divided by IB at silicon. That's the standard expression, right? In the absence of polysilicon, that's the standard expression I have. But because of this, say, polysilicon and silicon suppression of polysilicon, I have this extra factors on the very end, which has this red diffusion coefficient and small blue surface recombination velocity. So that ratio, I'm just plugging things back in from over the top, from the table or from the box on the top. Now, do you see that in this case, you can have a humongous gain? Because if Vs is small, then let's say it's close to 0, then on the term on the right, the numerator, the blue on the numerator will go to 0. But look at the denominator. There is a V sub s is sitting there, and therefore this could actually be significant. It could be a huge gain in this particular respect. And physically that makes sense. If your Vs is small, that means there is no whole current flowing to the base. So by even a tiny amount of base current, you can have a huge amount of collector current. And that's why this amplification is so large. And that's the point I wanted to make. Now again, just to tell you a quick story, that this came about accidentally, because the person who was supposed to grow this crystal, I mean, this is a sort of a story, it's a rumor story, but presumably it's true. The person, the technician who was supposed to grow the polysilicon or the silicon for the emitter, accidentally that reactor malfunctioned. So the temperature was not as high as it was supposed to be. The temperature was little lower. And therefore, instead of having the crystal, silicon crystal grown in the emitter, they accidentally had polysilicon grown. So they were actually planning to throw it away, right? Because, you know, there's a malfunction in the reactor, so better throw it away. But it turned out they just tested it. And amazingly, it turned out that that has a gain. The one that sort of malfunctioned with the malfunction reactor had a gain which was significantly better than anything they were making. As a result, this polysilicon transistor essentially subsequently become the standard in the industry. I have posted a paper on the website about the history, and you can take a look. And this is a very nice story about this whole thing. Okay, so do you understand physically? Forget about the math. Yeah, this is high school algebra. But the polysilicon, how it suppresses the base current by slowing down the holes, and as a result increases the gain. And subsequently after 1980s, this became the standard in the industry. But of course, like all good things, it comes to an end. And it came to an end sort of, I would say, in mid-90s or early 2000, when, so this game went on for a while. So they got a lot of gain, and then gradually they started shrinking the base over a period of time to get more and more gain. But at some point, you cannot play that game anymore for this reason. For the same reason. In fact, it's flip side of the same reason. So this is the gain I have for the polysilicon. Do you see in the end I have 1 over V sub s? That gives me the huge gain for the polysilicon transistor. Now let me tell you about the base transport and how, in fact, that term over time got poorer, not better but poorer, and that limits the gain in the following way. You see, if you make the base very small, so it started with, let's say, several hundreds of microns in the beginning, gradually you're making the base smaller and smaller. Why do you make it smaller? Because remember, the base width is in the denominator, because shorter the base width, more the gradient, faster is the current, and therefore more gain. Now if you keep making it smaller and smaller and smaller, the diffusion velocity, which is d over wb, will keep increasing, right? Because the gradient is more, it will go away faster. But there is a point beyond which electrons cannot go any faster. Even if it doesn't have any scattering, there is a maximum velocity electron can go, and that's called the saturation velocity. You cannot, electrons, even if it didn't scatter, ballistically went from one side to the other, it will not go any faster. As a result, when you make the base very, very, very small, in that case, the maximum velocity it can get out of the base is this V thermal velocity. Now I'll explain in a second why I didn't talk about it before, but let me first get you an expression for it. So now, instead of the current being simply N1 divided by WB and the other side being equal to 0, because I have finite velocity on the collector side, I will have this V thermal multiplied by N2, because that is the velocity at which electrons can escape, and it cannot go any faster. Again, I will do the same game, see, N2 over N1, I have the same ratio just like before, 5 minutes before. And correspondingly, I will have this, if it is ballistic, if the transport is ballistic, then I will have the same ratio, just like in the polysilicon I had it. I had a finite velocity in the polysilicon, I have a finite velocity in the ballistic transport case. So I have the same ratio, exactly the same thing. But this time it's bad. I'll explain. First of all, you see, okay, so let me get to the next slide. So I'll play the same ratio. I'm just copying it from the previous slide, but let me write this out and see whether you agree. So let's go slow. So first is that if I have both polysilicon and the base is so short that electrons are zipping through it ballistically, no scattering, no diffusion coefficient, right? Diffusion coefficient requires scattering. No diffusion, no scattering, no diffusion coefficient, electrons zipping through, then do you agree that I could split it up into 3 pieces? So I could compare how the ballistic collector current compares IC ballistic divided by IC silicon when it's not ballistic. So I can think about that. Then I can see how the collector silicon, normal standard, the green part, how it relates to the base current, you know, the classical one. And finally, I can see how the base current in the standard classical transistor is related to that one in the poly. You see, if you cross multiply, you will see that exactly what I have written, IC comma ballistic and IB poly is exactly the same thing. I just expanded it out. No rocket science here. So I will just copy those expressions. Now, if I copy this expression, do you see the symmetry in the third term and in the first term, right? Look, in one case I have V sub S in the denominator, in another case I have V thermal on the numerator, right? Because it's the same finite velocity and the corresponding diffusion coefficient come into play. Now what will happen? Let's see what will happen. So let's say my V sub S is very small. Okay, so if my V sub S is very small, then in the third term on the right, in the equation, preceding equation, V sub S, the blue one, is negligible compared to the red one. So I will drop that term and correspondingly bring it in. But look at the first term. If my V thermal is much smaller than the diffusion one, this is in the black, the first term, in that case what will happen? Correspondingly, exactly the same way, I have to drop V thermal, and the magenta V thermal on the numerator, that is the only one that's going to survive. As a result, you can see now the gain is given by the ratio of the thermal velocity divided by the surface recombination velocity. Now, thermal velocity is a material constant. If it is silicon, you have a thermal velocity. Therefore, you can see there's no more place to go. If you decrease your base anymore, you see, you cannot get any more gain. Now, does this sort of does it go with what I had been saying before? Before, what happened that the diffusion coefficient for the electron, d over WB, when WB was large, in that case, that was a small quantity compared to V thermal in the first term, in the magenta one. And so generally in the long base transistors, d over WB, you drop that. If you drop that one, then V thermal on the numerator, V thermal on the denominator, so that will give you 1. And that is the standard transistor. However, in this case, as you make the base width smaller and smaller and smaller, at some point, you get no benefit by making it any smaller or any thinner. And that is what happened in mid-90s. In fact, and that is the point beyond which they have not scaled the base width anymore, about 100 to 200 angstrom in the highest performance transistors today. Now, I will go through the frequency response. These are all about DC characteristics. But simply because you have a very significant gain of a transistor does not mean that you have a great transistor. And that is what I want to explain in the next few slides. So this will be a small signal. Now this will require some following through. So please pay attention and then we will see whether you can understand it. You may have to go back home and read it one more time. So what I want to know is actually I have a great DC gain that it amplifies the DC current well, but do I have a great AC gain? That is, if I have a small signal coming from a radio station, what is the highest frequency that I can amplify? If you try to do that, what you will see that when your frequency is low, that's the red curve, and you know x-axis is f, y-axis is log of gain. When the frequency is low, the DC one, well, that's great. You have a lot of gain. So it could be 100 or 1,000. But as you try to amplify more and more higher and higher signal, then what's going to happen? That then at some point the gain is going to drop like a stone towards the end, because it's a log plot, say. And even for 1 order of change in the frequency, there may be a factor of 10 decrease in the gain. So you started with 100. Now if your frequency gain is all of a sudden 10 and very soon 1, then you don't have a transistor anymore. You cannot catch the corresponding radio signal or signal you're trying to catch, let's say wireless signal, and amplify it anymore. So let's say, what is the cell phone signals these days? Do you know? This is about 2.4 gigahertz, right? So 2.4 gigahertz or so, that's the cell phone transmission band. So you have to design a transistor, let's say, which at least amplifies comfortably up to that frequency. So your f sub beta, at the point up to which things are flat, must be 2.4 in this case. If it are for some other application, then it may be lower or higher. So the question is, what determines f sub beta, or what determines f sub t when the gain becomes 1? That's what I want to know. And the thing I'm going to derive in next 20 minutes is this complicated looking expression, that it depends on many things. You see on the left hand side I have 1 over ft. So I want to calculate ft, so I have 1 over ft. And do you see on the right hand side I have a bunch of things. I have the base width. So I want to make this thing as small as possible, then 1 over ft will be large, right? Or sorry, ft will be large, and so if I make wb small, then that enhances my frequency performance. There are a bunch of capacitances. Do you see that these are all junction capacitances? Those are also very important on the second hand side, on the right hand side. Do you see IC somewhere? Second term on the denominator. If I could have a lot of IC, if I can forward bias it with a very high IC, then the second term will gradually drop out. And as a result, the whole sum will become smaller. And as a result, I will have a larger FT, right? So for larger FT, I should have as high a current as possible, as low a capacitance as possible, as thin a base as possible, right? So these are the things I want. Now, how does this expression come about? So let's see how it comes about. Now, if you did your homework, and or at least the one that I suggested in the class, then you might remember that if you take the Ebers-Moll model, which I drew it in the common base configuration, and convert it to a common emitter configuration, do you remember few class down? Then you should have this particular circuit where you had 2 diodes, one going from the base to the collector is on the other side, and another, the C pi and C mu are essentially the capacitances, various junction capacitances. So this is something you should have had. If you don't know how to do this, perhaps you will go back and look at that one more time. But for the time being, assume that this is what it is. Let's proceed with this one. Now, this is a DC equivalent circuit, or DC, or this is a generic equivalent circuit. I'm only interested in small signal equivalent circuit. So therefore, I can simplify this significantly more in the following way. First of all, I drop that diode. Why do we do that? Because of course it is a reverse bias junction. Tiny amount of current is flowing, right? Base to collector, isn't it reverse bias? Tiny amount of current is flowing. That diode isn't important. I drop it. But of course, I shouldn't drop the capacitances. The capacitances are still important. Okay. Now, after I have dropped it, first of all, look very quickly, C pi in both cases, C mu, do you see on the right hand side it's about the same. Only thing, the first diode, I have replaced it with R sub pi. That's one thing I have done. And the last current source, I have replaced it with Gm multiplied by VBE. How did I do that? In the following way. You know that the forward current is IF naught and the exponential of that, we know that. So first of all, let's see, I have a small signal. So I'm changing the base current a little bit, right? With a little bit on top of the DC bias. So I must know how is my base current changing with respect to VBE. As my input signal is changing, how is my base current changing? So if I take a derivative, then do you see that IB is essentially 1 minus alpha F multiplied by IF? Because I don't have that diode. So all the DC current or any current that is flowing in through the diode itself, right? So therefore, that's my base current. So I have 1 minus alpha F multiplied by IF. Now, do you see if you take a derivative of IF with respect to VBE, look at the expression on the very left. Then what do you pull out? A Q over KT. Do you see that? Over in the left, you pull out a Q over KT. And so that's what you see. If you pull out a Q over KT, so 1 over R pi is QIB multiplied by KT. No problem. This is simple. And IB, you could write it as IC divided by beta DC. Other than that, this is exactly the same expression. What about GM, the transconductance? Well, you could again calculate alpha F multiplied by IF. Why do I just talk about alpha F multiplied by IF? I'm talking about the current source. What is the value of IR in the blue, in the equivalent? IR is 0, right? Where it's reverse biased. So the only part in the blue current source is alpha F IF. So therefore, in the transconductance, I'm just taking with that with respect to VBE. Again, you take the derivative. If you take a derivative, you pick up a 1 over KT, Q over KT, and that's your final expression. And so, if you wanted to know how does the current source change when you change your base signal a little bit, then you will just cross multiply and write it as GM multiplied by VBE. And that's what is done in the equivalent, small signal equivalent circuit on the top, this magenta on the top. Okay, so I have that. This circuit, you know, even second year student undergraduate could solve, right? Hopefully, if you haven't forgotten. So let's see how to solve this one. Now, the way you solve this one is what you call a short circuit current gain. So you will short the emitter to the collector without any load, and you want to know how much current would flow when I send in a little bit of base current. How much current will flow from emitter to the collector, to the output circuit. That's the dotted line. I could write it in one sentence. IC over IB. Look at IC first. IC has this two current component, right? When the current is coming in, one is this current source going down, GMVB. That's one piece. And another is flowing through the capacitances. What is that? Capacitance is impedance J omega C multiplied by the voltage difference, which is the collector to base voltage difference. Do you see on the numerator I have VCB and multiplied by C mu. So that's what I have on the numerator. Now on the denominator, IB has these three components. One component is VBE divided by R pi. That's the first term on the numerator. Second term is I have a C pi and it will again be multiplied by VBE, and that's my second term. And do you see what the third term is? C mu multiplied by VBC. That's the third term. That's it. There's nothing more there. Two nodes and a few element circuit here. How simple can it be? So then I want to know, this is my gain at any frequency. You see, as you change your omega, this ratio will keep changing, and as a result, my gain will be changing. Now, at what point does the gain go from 100 to roll off and then become 1? That whatever input signal I put, I don't get any amplification. So that is the point when I'll call that frequency f sub t, and that must be equal to 1, right, by definition. So I want to know at what f sub t will my gain become 1. Now, do you see that the expression I have from the top. I'm just taking the absolute value. Now, given normal transistors, the C mu term on the top, the capacitance term on the top is generally small. Now, there's no reason, a priori reason. That is, people have historically have seen. So, you drop that term. So, you only keep Gm. And similarly, 1 over R pi, which is forward biased diode current, that's small. So, you drop that one also. So, you have that particular frequency. So, that's my answer. I have 1 over omega t, 1 over 2 pi ft is equal to C pi plus C mu divided by Gm. It looks nothing like the long expression that I am after. Remember that long expression I told you about a few seconds ago. But it will become that long expression in a few minutes. Because the Gm 2 minutes ago in the previous slide, I showed you that is kT over QIC. First thing. So that you can see that that's the term in the red. Okay. The C pi and C mu, these are junction and diffusion capacitances. Do you remember the diode equivalent circuit, that there was a diffusion capacitance, there was a junction capacitance? Do you remember? So I have just split it up. Cj is the junction capacitance, Cg is the diffusion capacitance. I have two junctions, I have two capacitances. Done. Now, the collector side, I do not have any diffusion capacitance, right? Why not? Because this is reverse bias, heavily reverse bias. I do not have many minority carriers. So I will drop this term. So I will drop that term. I'm sorry, I should have dropped the other term, this term, not this one. And correspondingly, so you have that first term, that is already in the final expression, I have that. So I will just leave it alone. This one somehow will become W squared divided by 2D and other things. So I will see how that becomes. But before I do that, let me convince you that the capacitance divided by the current, that can be written as the QB divided by IC. Do you agree with this statement? Because you can see that QIC divided by KT, couldn't I write it as DIC over DVB? Remember, that is how I pulled out Q over KT a few seconds ago. And if I flip DVE on the denominator, in the numerator, then C multiplied by V, what is that? That's the charge. So therefore, this becomes the charge because I have flipped this voltage up in here. And so this becomes the charge and DIC comes in here. So instead of calculating the diffusion capacitance and all, I could just evaluate this quantity and that will give me the second term, the rate term on the right. But let's see how to calculate that. That's easier. Now, in order to do this, this is where you need the charge control model. So the charge control model, if you go back, you will see during DC conditions, dQIB divided by DIC is essentially just QB over IC. Let's see whether you agree. This we did in the class before, did I? QB, Q sub B, is the area under the triangle. Is it ballistic? Do you think this is ballistic transistor? Not really, right? You see, because it's a classical transistor. On the other side, for the green triangle has gone to 0. Had it been ballistic, then it wouldn't have gone to 0. It would have moved with a certain velocity. But anyway, so you will have this area under the triangle, that's your QB, and the current IC, well, Ni divided by WB. So you see, the expression I got is essentially WB squared divided by 2dn. This is a very famous expression because this tells you how short, when you make the base small, how short the base transit time is. There's one more piece and then we are done. You see, so once it comes the end of that base collector junction, or then it has to traverse this huge depletion region. Very high field, and electrons will go with the saturation velocity through that junction. How long does it take? Is it simply WBC divided by VSAT? Not really. Do you remember the image charge we talked about a few days ago, right? If you have image charge, then it will go slightly faster. And what is going to happen that as soon as the red electron gets into the depletion region, it will be imaged on the collector side. And as a result, the current will begin flowing even when the red electron has not arrived to the collector. As a result, the current would look like a triangle. But of course, at the end of the day, you have only transferred the charge Q. So you have half multiplied by I is the current, and that's changing with time, multiplied by tau, the average time for the electrons to go, that must be equal to Q. And as a result, the time it takes for the electrons to collect that depletion region is WBC over 2 VSAT. It goes a little faster because the image charge on the collector essentially pulls it in, sort of. And so it goes a little faster than you would have otherwise expected. Okay, so I'm done. You can see the junction capacitance part, right? Remember the junction capacitance part? In the denominator part, in the first part, this is the dQB divided by DIC. Two pieces, how long it takes for the electrons to go through the base and how long it takes for the electron to go through this depletion region. Add them up, that's the whole thing. As a result, what happens that when you begin to increase the collector current, the I sub C, let's say you're increasing it, the second term begins to drop because you can charge the capacitance fast. You have a lot of current flow. So you can charge the capacitance first, and so second term begins to go small, and your 1 over Ft becomes gradually smaller, Ft becomes larger. So you can see the frequency is gradually increasing as you make the collector current more. However, what happens if you push too much collector current? At some point, it overwhelms the collector doping. Do you remember what is that effect called? Kark effect, right? Where it overwhelms it. And the base used to be WB, this tiny region. And when so many electrons sort of has flooded in, it has destroyed the junction. And as a result, the base has been pushed out all the way to the subcollector. Now I have this humongous base instead of the tiny one, right? As a result, my WB at some point when I make IC too big, my WB will be so big that any advantage that I had here will be compensated, overcompensated by the first term. As a result, my frequency will begin to drop because I require now more time. This whole thing has to go through this long pushed out base. This is exactly what happened in mid-60s, and Kark, people used to make this transistor, measured them in their lab, and all well they will see a turnover. Nobody understood it. The best mind at that time, you know, all this big industrial lab, they had Sony, they had IBM, they had TI, scientists are looking all over that what could it be that I cannot push my frequency anymore? And Kark explained that effect, and that's why the effect is named after him. He explained it because he was the first one to suggest that how excessive collector current can overwhelm WB, and as a result, it will roll over. So it's called I sub k, that's the Kark current. So in general, I told you about all those things. Tau sub b is W squared divided by 2D, and the collector transit time is WBC divided by 2 VSAT, that's fine. Generally, people have to add this extrinsic resistance, the resistances that you have from outside, that becomes an important part also. So that's something one has to check. And also sometimes you are interested in maximum power gain, not only the frequency gain. I'll not derive that, but that can be calculated as shown in the bottom expression. So let me summarize. So the basic idea is that the basic transistor, the standard transistors of 1950s, have actually gone through many modifications. Most important of them are this polysilicon transistor, right? That was a great innovation. Without it, transistor scaling, bipolar, would have stopped at 1980s because things have stopped by then. But it was 15 more good years because of 15 to 20 more good years because of the polysilicon, but then the short base essentially killed it because you cannot improve it any further. You do not have any more gain. So these days people play with the junction capacitances. They try to make it as small as possible by making good isolation and other things, thereby increase the frequency. Now I showed you how to do the small signal. I made a lot of uses of the diode results. So if you didn't understand diode results properly, this is the time to go back and review them. That will make things clear because I assume that you know, but hopefully it will become clear with time. Now, the bottom line is at the end is that classical homojunction transistors can only go so far, and nowadays then heterojunction bipolar transistor has essentially replaced the technology, and in the next two classes I will tell you how heterojunction bipolar transistor works. Okay. Now, I have 3 slides as an aside on collector base breakdown voltages that I want to cover. One thing I have not discussed is what happens when you apply a large bias in the collector. Now you can see the base collector junction is essentially a diode. When you apply a large bias on a diode, what happens? Eventually it breaks down, and it breaks down by 2 methods, right? What are those? Zener tunneling, electrons could tunnel from the base to the collector, or impact ionization. It could break both ways. I want to explain to you why the breakdown of a bipolar junction transistor is a little bit more complicated, slightly more complicated than a simple PN junction, because there is an extra amplification involved. Let me explain. First, let me explain what is the essence of current gain in a bipolar transistor in a very simple way. You see, this is a common emitter configuration, right? You put a base current, certain amount of base current, let's say, and the base current flows out through the emitter. That's what happens. That's the blue arrows. Now, the way to think about it is, you know the expressions for the base current. You have a bunch of constant, but the main thing is you have a QVBI, beta is 1 over kT, QVBI minus 1. So when you push a base current, then the transistor must accept that current because you are forcing it to. Only way it can accept the current, that it will keep lowering the barrier in the base emitter side until it has lowered the barrier enough so that the whatever whole current you are putting in through that blue triangle, up triangle, that can flow out to the emitter. So you are forcing, your input is base current, you are forcing a voltage in response. Now, when you force a voltage in response, what it does, it forward biases the junction, and the electrons are just sitting there. It says, well, my barrier is lowered, and so electrons decides to go on its own. So now you can see, for electrons, the VBE becomes the input because the barrier has been forward biased, so the current will flow. And as a result, you can see that red arrow going from the emitter to the collector region. So therefore, this is how the base current controls the collector current. This is how the gain occurs, right? Now, if you understand this part, now you will understand why the breakdown is fundamentally different in various base configuration, various transistor configuration. Let's first talk about the case where there is a common base configuration. Now, in a common base configuration, the emitter current is constant. I fix the emitter current. In that case, how will the breakdown occur? I have used a large collector bias. You can see a huge difference and a large electric field on the base collector junction. Again, the base current will come in. It will forward bias the junction. Current will flow over. Now it will, once it starts getting into the collector region, it has tremendous amount of electric field. As a result, there will be impact ionization, right? There'll be how much energy do you need? Approximately 3/2 the band gap. You cannot have just the band gap, a little bit more. 3/2 the band gap, let's say. And as a result, you will, the green one is the second electron that has been generated, sort of. And the red one that you see are extra holes that have been generated. Now, the holes like to float up, right? These are like bubbles, so it floats up. Now, the thing is, the collector current, it doesn't want anymore because that's the common base configuration. So, in that case, it will get out through the base. Base current is not controlled. As a result, this breakdown completely depends on the base emitter voltage, base collector voltage. It doesn't care about what is happening to the emitter. The larger voltage that you apply on the base collector side, that's when the breakdown occurs. This in contrast with the next thing. The next thing is common emitter configuration. In common emitter configuration, the figure on the right shows the IV characteristics. It breaks down much more easily. Do you remember it has a lot of gain, right? IC over IB, beta, lot of gain. But you see the problem with this, because this breaks down much more easily, and this is why. Look at that. Again, current coming in, base current coming in, flowing out through the emitter, no problem. Electron flowing in, trying to impact ionize. But now this time, base current is fixed because this is a common emitter configuration. Base current is fixed, so these extra holes that are coming in, the base doesn't want it anymore. Base has already decided how much current it can have. As a result, it cannot have that. As a result, the base, this excess current that has been generated now must get out through the emitter. Now, the more emitter current it has to push, what will happen to VBE? Now, the VBE must be larger, or that the barrier must be reduced so that it can accept that current, right? As soon as it reduces the barrier, what will happen? That correspondingly, it will forward bias the junction, more electrons will flood in, and more electrons flooding in means more impact ionization. Very soon, because of the presence of that first barrier, first PN diode, the breakdown will occur very quickly. And you can see on the right hand side that how much faster. It's almost begin to break down at a very low voltage. Even by the 20 volts, gradually currents are increasing quite a bit. So this is a very important distinction between just a single diode versus a bipolar transistor, and that is something that you should remember. Okay? And this is the basic point about breakdown voltage. That's it. Thanks.